Right now, the James Webb Space Telescope is staring into a darkness so deep that the light reaching its mirrors left its source over 13 billion years ago, and what it found there was not what anyone predicted. Galaxies that should not exist, structure that arrived too early, a universe expanding at two different speeds depending on where you measure it. Scientists expected Webb to extend the map. Instead, it broke the map. The true scale of the universe is not just bigger than you imagined, it is stranger than your imagination can process. And the deeper Webb looks, the less our picture of cosmic history holds together. What you are about to hear will permanently change how you understand the place you exist in, and it raises questions that do not yet have answers. If this kind of deep science is what you come here for, hit like and subscribe. It genuinely helps more than you think, and it means we get to keep making these. Now, are you comfortable? Let's begin. Most people believe they understand how big the universe is. They do not. What they understand is a feeling, a vague sense of enormousness that washes over them whenever someone mentions the word billion or shows them a photograph of a galaxy cluster. They nod, they say the right things, they tell themselves they get it. But what they actually possess is not understanding. It is a defense mechanism, a way of absorbing an incomprehensible fact by flattening it into a comfortable abstraction. The universe is really, really big. That sentence has become a kind of cultural password. Say it with enough confidence and nobody asks what you actually mean by it. Nobody asks you to sit with the number. Nobody asks you to feel it rather than repeat it. And that is exactly where the problem begins. Because until you move past the comfortable version of cosmic scale, you cannot begin to understand why James Webb changed everything. And it did change everything. Not by making the universe bigger, by making bigness itself feel unstable. Let us start where most people start, with Earth. Earth feels large when you are standing on it. It takes more than a day to fly from one side to the other. Entire civilizations rose and fell, without ever knowing what lay beyond their own coastline. For most of human history, the planet was the universe. Everything that mattered, everything that existed, as far as anyone could prove, was here. The ground beneath you, the sky above, and whatever you could reach by walking or sailing. That was the whole picture. Then we measured it. The circumference of Earth is roughly 24,900 miles. That number is big enough to feel significant when you say it out loud, but it becomes small almost immediately when you place it next to anything else. The Moon sits about 239,000 miles away. That is roughly 30 Earths lined up side by side. If you could drive a car at highway speed without stopping, it would take you roughly 5 months to reach it. That is already further than most human minds want to travel in imagination. But the Moon is close. In cosmic terms, it is so close it is practically sitting on your lap. The Sun is about 93 million miles from Earth. Light, the fastest thing in the universe, covers that distance in roughly 8 minutes and 20 seconds. Every time you look at the Sun, you are seeing it as it was 8 minutes ago. If it vanished this instant, you would not know for another 8 minutes and 20 seconds. You would feel the warmth. You would see the light. And all of it would be a ghost. That idea alone is enough to make most people uncomfortable if they sit with it long enough. But the Sun is still local. It is still neighborhood. The nearest star beyond our Sun is Proxima Centauri, sitting approximately 4¼ light years away. A light year is the distance light travels in 1 year, moving at roughly 186,000 miles per second. That works out to about 5.88 trillion miles per light year. Multiply that by 4¼ and you arrive at a number so large it stops functioning as a number. It becomes a symbol, a placeholder for something your brain cannot hold. If you launched a spacecraft at the speed of the fastest human-made object ever sent into deep space, the Parker Solar Probe, at its peak velocity of roughly 430,000 miles per hour, it would take you roughly 6,500 years to reach Proxima Centauri. That is longer than all of recorded human civilization. You would depart as a species that just invented writing and arrive as something unrecognizable, if you arrived at all, and you would have crossed the gap to one star, the nearest one, in a galaxy that contains somewhere between 200 billion and 400 billion of them. This is the point in the scale conversation where most people quietly check out. Not obviously, not rudely. They simply stop building the picture and start accepting the label instead. The Milky Way is big. They file it away. They move on, but you should not move on, because this is where the texture of scale starts to matter and where the comfortable version of the story begins to quietly fall apart. The Milky Way galaxy is a barred spiral, roughly 100,000 light-years across. If you could somehow stand outside it and look down, you would see a vast pinwheel of stars, gas, and dust rotating around a central core. Our Sun sits roughly 26,000 light-years from that center, about halfway out along one of the spiral arms. We are not in a special position. We are suburban. A mid-range star, in a mid-range location, in a mid-range arm of a galaxy that is itself mid-range in size. Now try to imagine the distance from one side of the Milky Way to the other. 100,000 light-years. Light, moving at the fastest speed the universe permits, takes 100,000 years to make that crossing. When the light arriving at one edge of our galaxy today left the other edge, human beings on Earth had not yet invented agriculture. They were painting animals on cave walls and surviving ice ages. That is one galaxy. And it is not even a large one. The nearest major galaxy to ours is Andromeda, roughly 2.5 million light-years away. The light you see when you look at Andromeda left that galaxy when the very first members of our genus were just appearing on Earth. You are looking at a ghost image from before your species had a name. And Andromeda is a neighbor. It is part of what astronomers call the local group, a small gravitational family of more than 50 galaxies clustered together in a region roughly 10 million light-years across. That cluster is itself a tiny suburb within the Virgo supercluster, which spans roughly 110 million light-years. And the Virgo supercluster is one small corner of Laniakea, a supercluster of superclusters spanning over 500 million light-years, containing roughly 100,000 galaxies. This is usually the moment in a documentary where someone tells you there are around 2 trillion galaxies in the observable universe. And you nod. 2 trillion. Fine. The number enters your mind, touches nothing, and exits cleanly. It is too big to mean anything, so it means nothing. And that is the exact problem James Webb is about to expose. But before we get to Webb, there is a critical concept that most people have heard of, but almost nobody truly absorbs. And without it, nothing about the scale of the universe makes real sense. Distance in space is not just distance, it is time. When you look at the moon, you see it as it was 1.3 seconds ago. When you look at the sun, you see it as it was about 8 minutes and 20 seconds ago. When you look at the Andromeda galaxy, you see it as it was 2.5 million years ago. The light from Andromeda has been traveling toward Earth for longer than modern humans have existed. You are not seeing Andromeda. You are seeing a memory of Andromeda, encoded in photons that left before you were a biological possibility. This works in every direction. Every object you observe in the night sky is a window into the past. The farther away something is, the further back in time you are looking. A galaxy 10 billion light-years away is not just far, it is old. You are seeing it as it was 10 billion years ago, when the universe itself was only a few billion years old. You are watching a scene from cosmic childhood. This means telescopes are not simply cameras that photograph distant places, they are time machines. Every improvement in telescope range is also an improvement in time depth. When astronomers build a bigger mirror, a more sensitive detector, or a telescope that can see in wavelengths of light that older instruments could not detect, they are not just seeing farther across space. They are seeing deeper into the past. And the deeper you look, the younger the universe you are observing. At the very edge of what any telescope can see, you approach the beginning, the first light, the first structures. The moment when the universe transitioned from a hot, opaque fog of particles into something transparent enough for light to travel freely. That moment happened roughly 380,000 years after the Big Bang. It is called recombination. Before it, the universe was so hot and dense that photons could not travel in a straight line. They scattered off free electrons in every direction, like headlights in thick fog. After it, the universe cooled enough for electrons to combine with protons and form neutral atoms. The fog lifted. Light was free, and that first freed light is still traveling. It fills the entire sky. It has been detected and mapped with extraordinary precision. Scientists call it the cosmic microwave background radiation. It is the oldest light in the universe. And it is not just old, it is the boundary. Beyond it, there is no light to see. Before it, the universe was dark. Take a moment to absorb what that boundary means. When you look at the cosmic microwave background, you are not looking at a distant object. You are looking at a wall. A wall made of light, radiating in every direction, completely surrounding the observable universe like the inner surface of an enormous sphere. That light was released when the universe was 380,000 years old. It has been traveling ever since. And because it comes from every direction equally, it defines the ultimate horizon of observation. There is no telescope that will ever see beyond it using electromagnetic radiation, because beyond it there was no free light to collect. The universe before recombination was opaque. Photons could not travel in straight lines. Information from that epoch is locked behind a wall of fog that no optical or infrared or radio instrument can penetrate. This is a hard boundary, not a technological limitation that a better telescope could overcome, a physical limitation imposed by the nature of light and the history of the cosmos. Everything we know about the universe from direct observation is confined to the volume inside that wall. The first 380,000 years of cosmic history, including the Big Bang itself, are accessible only through indirect methods, the faint imprints left on the cosmic microwave background, the ratios of light elements forged in the first few minutes, and the gravitational signatures of structures that began forming before the fog lifted. What sits between that wall and the present day is the entire visible history of the cosmos, 13.4 billion years of evolution. From the first atoms to the first stars to the first galaxies to the intricate web of structure we see today. Every telescope ever built has been exploring some portion of that interval. And until recently, the picture that emerged from those explorations was remarkably coherent. The cosmic microwave background provided the initial conditions. It showed a universe that was almost perfectly uniform, but not quite. Tiny fluctuations in temperature, variations of roughly 1 part in 100,000, revealed slight differences in the density of matter at that early moment. Those density differences were the seeds. Regions that were slightly denser than average would attract more matter through gravity. Over hundreds of millions of years, those regions would grow, collapse, and form the first stars and galaxies. Regions that were slightly less dense would become the vast empty voids that separate the galaxy clusters today. This prediction was not vague, It was quantitative. Scientists could measure the pattern of fluctuations in the cosmic microwave background, feed those measurements into the equations of the Standard Model, and calculate what the universe should look like at every subsequent epoch. How many galaxies should exist at a given time, how large they should be, how they should be distributed across space. The model produced specific numbers that could be checked against observations. And for decades, the checks passed. The distribution of galaxies at moderate distances matched the predictions. The abundance of light elements, hydrogen, helium, and trace amounts of lithium matched the calculations for what should have been produced in the first few minutes after the Big Bang. The relationship between the distance of a galaxy and its recession velocity followed the expected curve. The large-scale structure of the cosmos, the filaments and walls and voids that organize matter on scales of hundreds of millions of light-years, matched the patterns predicted by simulations that started from the initial conditions encoded in the cosmic microwave background. Each confirmation strengthened the framework. Each successful prediction added weight to the conclusion that lambda CDM was not just a useful approximation, but a fundamentally correct description of the universe's composition and evolution. By the early 2010s, the model had been tested so thoroughly and confirmed so consistently that cosmology experienced something unusual in the history of science, a sense of near completion. Not the arrogant claim that everything was understood, but a quieter, more pervasive confidence that the remaining questions were questions of detail rather than questions of foundation. The broad strokes were settled. The age was known, the composition was known, the expansion history was known, the geometry was known. What remained was filling in the fine print, the specifics of how galaxies assembled, how stars formed in different environments, how the first light sources ignited in the darkness. Important questions, certainly, but questions that lived within the framework rather than threatening it. That confidence was the backdrop against which James Webb was designed, built, and launched. Webb was conceived as a tool for answering detail questions. How did the first galaxies form? What did they look like? How did reionization proceed, the process by which the first light sources burned away the residual fog of neutral hydrogen that lingered after recombination? These were questions that assumed the Standard Model was correct and asked Webb to fill in the chapters that Hubble could not read. The framework was the foundation. Webb was supposed to furnish the rooms. Nobody expected it to find cracks in the foundation itself. For decades, the Hubble Space Telescope was the instrument that defined our view of the deep universe. Launched in 1990, repaired and upgraded multiple times by astronauts in orbit, Hubble became the most productive scientific instrument in human history. During its tenure, astronomers discovered that the universe is not just expanding, but accelerating in its expansion, driven by a mysterious force called dark energy. Hubble contributed to confirming and refining that finding, and it produced the Hubble Deep Field images, photographs of seemingly empty patches of sky that turned out to contain thousands of galaxies in every direction, each one a separate island of billions of stars. Hubble could see back to roughly 400 million years after the Big Bang in the most extreme cases. That was extraordinary. It gave us a picture of the universe's first billion years that felt, if not complete, at least consistent. The galaxies Hubble found at great distances were small, faint, irregular. They looked young. They looked like exactly what the models predicted. Baby galaxies, still assembling, still pulling together their first generations of stars. Everything fit. The Standard Model of cosmology, known as lambda CDM, described a universe that began in a hot, dense state, expanded, cooled, and gradually built complexity. First particles, then atoms, then gas clouds, then the first stars, then small galaxies that merged into larger ones over billions of years. The timeline was coherent. The predictions matched the observations. The cosmic microwave background provided a snapshot of the universe at age 380,000 years, and when scientists used that snapshot to calculate what the universe should look like today, the answer matched what telescopes actually saw. Not perfectly, not in every detail, but close enough that the framework was trusted. And embedded in that framework was a specific picture of cosmic scale. The observable universe, the sphere of space from which light has had time to reach us, has a diameter of roughly 93 billion light-years. That number sounds contradictory. How can the observable universe be 93 billion light-years across if the universe is only 13.8 billion years old? The answer is expansion. Space itself has been stretching since the Big Bang. The objects that emitted the oldest light we can see were much closer when that light departed, but space has been expanding beneath that light during its entire journey. By the time the light arrives, the objects that emitted it have been carried much farther away by the stretching of space itself. The edge of the observable universe is now roughly 46.5 billion light-years away in every direction, even though the light from that edge has only been traveling for 13.8 billion years. This is the standard picture. It is correct as far as it goes, and for most people, it is the end of the conversation about scale. The universe is 93 billion light-years across, contains roughly 2 trillion galaxies, is 13.8 billion years old, and is expanding. Big, old, expanding. Filed away, understood. Except it is not understood at all. It is labeled, and labeling something is not the same as understanding it. Labels are what we use when understanding fails. When a number is too large to feel, we name it and move on. When a distance is too vast to picture, we convert it into a comparison and treat the comparison as comprehension. The universe is really big. The sentence carries zero information beyond what you already felt. It is a linguistic shrug, a verbal emoji for awe that has been drained of actual awe. And this is the precise state of comfortable ignorance that most people were sitting in when the James Webb Space Telescope opened its eyes. Webb was not a surprise. It was planned, designed, debated, delayed, redesigned, and nearly cancelled across more than 2 decades of development. The project began in the mid-1990s as the Next Generation Space Telescope. It was renamed in 2002 after James E. Webb, the NASA administrator who led the agency during the critical Apollo years. Its projected cost grew from roughly $1 billion to nearly $10 billion by the time it launched. It became one of the most complex engineering projects in human history. It launched on December 25, 2021, aboard an Ariane 5 rocket from French Guiana. Over the following month, it executed a sequence of deployments so intricate and so dependent on perfection that engineers described it as having 344 single points of failure, any one of which could have ended the mission. Every single one succeeded. Webb traveled to a point in space called the second Lagrange point, or L2, roughly 1 million miles from Earth on the side opposite the Sun. At L2, the gravitational forces of the Earth and Sun balance in a way that allows Webb to orbit in a stable position, always keeping its sunshield pointed toward the Sun, while its instruments stare into the cold dark of deep space. The sunshield is the size of a tennis court. It consists of 5 layers of a material called kapton, each thinner than a human hair, separated by gaps that allow heat to radiate away between them. On the sun-facing side, the temperature reaches roughly 230 degrees Fahrenheit. On the instrument side, it drops to roughly minus 394 degrees Fahrenheit. That temperature difference across the thickness of a few sheets of material is what makes Webb's observations possible. The reason Webb needs to be so cold is the same reason it exists at all. Webb sees in infrared. Infrared is light, with wavelengths longer than what the human eye can detect. It is the kind of light that warm objects emit. Your body emits infrared radiation right now. So does every piece of warm equipment on a spacecraft. If Webb's instruments were not cooled to extraordinary temperatures, they would be blinded by their own heat, unable to distinguish the faint infrared whispers of the distant universe from the thermal noise of the telescope itself. Why infrared? Because the universe is expanding. As space stretches, the light traveling through it stretches too. Light that was emitted as visible light or even ultraviolet light billions of years ago has been stretched during its journey until it now arrives as infrared. The older the light, the more it has been stretched. The most ancient light in the universe, the light from the first galaxies and the first stars, has been stretched so far into the infrared that no visible light telescope can detect it at all. Hubble had some infrared capability, but it was limited. Webb was designed from the ground up to see precisely the wavelengths where the oldest light now lives. This is what makes Webb fundamentally different from every telescope before it. Not just bigger mirrors, not just better resolution, a different kind of seeing. Webb can detect light that has been traveling for over 13 billion years, light that left its source when the universe was less than 300 million years old. And it can see that light with enough clarity and spectral detail to tell scientists not just that something is there, but what it is made of, how massive it is, how fast it is forming stars, and how its structure compares to what the models say should have been possible at that moment in cosmic history. That last capability is the one that matters most, because it turns distance into a test. Every time Webb looks deeper into space, it is also looking deeper into time. And every time it looks deeper into time, it is comparing what it sees against what the standard model of cosmology says should exist at that epoch. If the models are right, the observations should match. If the observations do not match, something in the model is wrong. Before Webb, most of the deep universe observations matched the models closely enough that the standard framework felt secure. The galaxies found at great distances were small and faint. The structures were primitive. The chemistry was simple. Everything pointed in one direction. A universe that built complexity gradually, from simple beginnings, over billions of years. Scale was just distance. Time was just age. And the further you looked, the simpler and younger everything appeared, exactly as predicted. That was the picture. It was coherent. It was comforting. It made the universe feel knowable, even if the numbers were too large to fully grasp. You could hold the story in your head. A universe that started hot and dense, expanded, cooled, built stars and galaxies slowly, and arrived at the complex cosmos we see today through a long, orderly process. Scale was a fact, a static measurement, something you could write down on a page and feel you had captured. Then Webb began sending back data, and within months, the picture started coming apart. Not dramatically, not in a single headline, but systematically, one observation at a time, one mismatch after another, in a pattern that is still building as of right now. The galaxies Webb found in the deep universe were not all small and faint. Some of them were massive, mature, structured in ways that should have taken billions of years to develop, yet existing when the universe was only a few 100 million years old. The chemistry was not always simple. Some early galaxies showed heavy elements, nitrogen and oxygen, at levels that implied generations of star formation had already occurred in a window of time that barely seemed large enough for a single generation. And the expansion rate of the universe, the number that anchors the entire framework, turned out to be in conflict with itself. Measured one way, it gives one answer. Measured another way, it gives a different answer. Webb confirmed that the discrepancy is not a measurement error. It is real. And It has now reached the level of statistical certainty that physicists use to declare a result genuine. None of this was supposed to happen. Webb was built to fill in details, to sharpen the image, to confirm the timeline with greater precision, and push the boundary of observation a little further into the past. Instead, it revealed that the past does not look the way the models said it should. The comfortable picture of cosmic scale, the one where distance is just distance, and time is just time, and everything gets simpler the further back you look, is not holding up under Webb's gaze. The map was supposed to get clearer. Instead, the territory turned out to be different from the map. And understanding why requires looking at what Webb actually sees, how it sees it, and what the specific observations mean for every assumption built into the standard picture of cosmic history. That is where the story goes next. Because what Webb has detected in the first few 100 million years of cosmic time is not just unexpected. It is forcing scientists to ask whether the framework they have trusted for decades is missing something fundamental. And the answer to that question changes what the scale of the universe actually means. Webb was built to sharpen the image. What it did instead was reveal that the image was wrong. The mirror is the first thing engineers will tell you about. 6.5 meters across, composed of 18 hexagonal segments, each one made of beryllium and coated in a layer of gold so thin that if you gathered all the gold on the entire mirror and pressed it into a single solid ball, it would be roughly the size of a marble. Gold was chosen for a specific reason. It reflects infrared light with extraordinary efficiency, better than 98% across the wavelengths Webb was designed to capture. Every photon matters when you are trying to detect objects that emitted their light over 13 billion years ago. You cannot afford to lose even 2% of what arrives. Each of the 18 mirror segments can be adjusted independently using tiny motors called actuators, capable of movements measured in nanometers. A nanometer is 1/1,000,000th of a meter. These adjustments allow the segments to act as a single continuous mirror with a collecting area roughly 6 times larger than Hubble's and the ability to focus infrared light with a precision that no previous space observatory could. Approach. This is not just a matter of making images prettier. It is the difference between seeing a faint red smudge and seeing a faint red smudge clearly enough to break its light into a spectrum, identifying the chemical elements present, measuring the speed at which matter is moving, and determining whether the object is a galaxy, a black hole, a dying star, or something nobody has categorized yet. The instruments mounted behind that mirror are where the real science happens. 4 primary instruments divide the incoming light among them, each designed to answer a different type of question. The near-infrared camera, known as NIRCam, is the primary imaging instrument. It captures the deep-field photographs that reach the public, the ones filled with thousands of galaxies in every direction. But NIRCam does far more than take pictures. It operates across multiple infrared filters, allowing astronomers to photograph the same patch of sky at different wavelengths and compare the brightness of objects across those wavelengths. This technique, called photometry, is how scientists make their first estimates of an object's distance, age, and composition without needing to take a full spectrum. The near-infrared spectrograph, NIRSpec, is arguably the most revolutionary instrument on the telescope. It can take the light from a distant object and spread it into a rainbow of infrared wavelengths, revealing absorption and emission lines that correspond to specific chemical elements and physical conditions. When hydrogen is present, it leaves one kind of fingerprint. Oxygen leaves another, nitrogen another, carbon another. Each element absorbs and emits light at precise wavelengths, and those wavelengths shift depending on how fast the object is moving away from us, which directly tells you its distance. NIRSpec can observe up to roughly 100 objects simultaneously using a micro-shutter array. a grid of nearly 250,000 tiny shutters that open and close individually to select exactly which object's light enters the instrument. This allows astronomers to gather spectra from hundreds of galaxies in a single observation session, a process that would have taken Hubble decades to complete one galaxy at a time. But before we reach the instruments that probe the coldest and most obscured corners of the cosmos, it is worth pausing on something that the technical specifications alone cannot convey. The moment when Webb's first data arrived. On July 11th, 2022, the first full-color image from the James Webb Space Telescope was unveiled in a live broadcast from the White House. The image was called Webb's First Deep Field. It showed a galaxy cluster called S-MAX 0723, a massive gravitational structure sitting roughly 4.6 billion light-years from Earth. The cluster itself was not the point. The cluster was a lens. Its combined gravitational mass was so enormous that it warped the fabric of space-time around it, bending and magnifying the light of far more distant galaxies behind it. Those background galaxies, stretched and smeared into arcs and streaks by the warping of space, were the real targets. Some of them were among the most distant objects ever observed. The image covered a patch of sky roughly the size of a grain of sand held at arm's length, a speck, a negligible fraction of the total sky, and within that speck, thousands of galaxies were visible. Not dozens, not hundreds, thousands. Every smudge of light in the image was an entire galaxy, each one containing billions of stars, many of them surrounded by planets, all of them separated by distances so vast that light itself takes millions or billions of years to cross the gaps between them. And this was one grain of sand out of an entire sky. Hubble had imaged a similar region years earlier. The comparison was immediate and devastating. Where Hubble had seen a sparse field with a few hundred identifiable objects, Webb saw a dense tapestry of galaxies layered behind galaxies, receding into depths that Hubble could not reach. Objects that had been invisible smudges in Hubble's data resolved into structured galaxies with visible spiral arms, dust lanes, and companion satellites. Objects that had been completely absent from Hubble's images appeared for the first time, glowing faintly in infrared wavelengths that Hubble's instruments could not detect. Astronomers who had spent decades working with Hubble data described the experience of seeing Webb's first images in terms that were unusually emotional for a scientific community trained in measured language. Jane Rigby, the Webb Operations Project scientist at NASA, said the images were as sharp and as crisp as she had dreamed they would be, and then added that they exceeded expectations across the board. Thomas Zurbuchen, then NASA's Associate Administrator for Science, described the moment as one that would change the picture humanity has of itself. That sounds like rhetoric. It was not. Because the sheer density of galaxies in Webb's first images was itself a data point. The models predicted how many galaxies should be visible at each depth and in each wavelength range. The number Webb actually detected was higher, not catastrophically higher, not enough to break the models on day one, but noticeably, consistently, measurably higher than what the simulations said should be there. The surplus was strongest at the greatest distances among the faintest and reddest objects in the image, exactly the population that corresponds to the earliest epochs of cosmic history. That first image was a warning shot. The community registered it, noted the tension, and waited for more data. The more data arrived quickly, and it confirmed the pattern. The mid-infrared instrument, MIRI, extends Webb's vision into longer wavelengths that probe colder and more obscured objects. Dust, which blocks visible light and even some near-infrared light, becomes nearly transparent at mid-infrared wavelengths. MIRI can peer into star-forming regions shrouded in dense clouds, observe planets and their atmospheres, and detect the faint thermal glow of objects too cold for NIRCam to see clearly. MIRI operates at -266 degrees Celsius, only 7 degrees above absolute zero, achieved using a mechanical cryocooler that actively pumps heat away from the detector. That temperature is necessary because at mid-infrared wavelengths, even the instrument's own warmth would overwhelm the signal from distant cosmic sources. The fourth instrument, the fine guidance sensor, a near-infrared imager and slitless spectrograph, handles both navigation and a unique form of spectroscopy that captures spectra from every object in the field of view simultaneously, useful for surveying large areas efficiently. Together, these four instruments give Webb something no telescope has ever had before: the ability to detect, image, and chemically analyze objects from the earliest epochs of cosmic history with enough precision to challenge or confirm the predictions of the Standard Model. Hubble could see a faint red dot at extreme distance and estimate how far away it might be based on its color. Webb can see that same dot, resolve its structure, break its light into a detailed spectrum, measure the abundances of individual elements, determine whether its brightness comes from stars or from a feeding black hole, and compare all of those measurements against the specific expectations of lambda CDM. That capability is what made the first years of Webb's operation so disorienting for the scientific community. Because the comparisons kept failing, the trouble started almost immediately. Within the first months of science operations in 2022, teams analyzing Webb's initial deep field images began reporting objects that did not match expectations. The Cosmic Evolution Early Release Science Survey, known as SEERS, targeted a seemingly empty patch of sky that overlapped with existing Hubble imaging. The idea was to use Webb's infrared vision to see what Hubble had missed, to push the observations deeper into the universe's first billion years and catalogue the tiny, faint galaxies that should have been there. They were there, but they were not tiny, and they were not faint. An astrophysicist named Erica Nelson was among the first to spot the problem. Examining postage stamp-sized sections of the SEERS images, she identified several objects that appeared as fuzzy red dots. Red because their light had been stretched by the expansion of space across more than 13 billion years of travel. Fuzzy because even Webb cannot produce crystal-clear portraits at those distances. But anomalously bright, far too bright. These objects were radiating at levels that implied enormous stellar masses, the kind of masses that should not have had time to assemble so early in cosmic history. The team ran the numbers. Each object appeared to contain somewhere between 10 billion and 100 billion solar masses worth of stars. For context, the Milky Way contains roughly the same range. These objects were rivaling our entire galaxy in stellar mass, while existing when the universe was only about 500 to 700 million years old, just 3 to 5% of its current age. Nelson and her colleagues gave them a nickname: universe breakers. Because if the masses and distances held up, these galaxies directly contradicted the predictions of the standard cosmological model. There simply had not been enough time since the Big Bang for that much matter to collapse into stars, especially not in the quantities these images suggested. The models said the early universe should have been populated by small, irregular proto-galaxies slowly assembling their first stellar populations. What Webb appeared to be showing was mature galactic structures, fully formed, bright, and massive, existing at an epoch when the universe should have been barely getting started. The immediate response was appropriate scientific caution. The photometric estimates could be wrong. Webb's instruments were still being calibrated during those early observations. The technique used to estimate distance based on color, called the dropout method, is powerful but imperfect. An object that appears extremely distant based on its colors could potentially be a closer, unusual object that mimics the color signature of extreme distance. Confirmation would require spectra, the detailed chemical fingerprints that NIRSpec could provide. Spectra began arriving over the following months. Some of the original universe breakers turned out to be less extreme than first thought. At least one was revealed to be a closer galaxy hosting an actively feeding supermassive black hole, which made it appear brighter and more massive than it actually was. That was important. It showed that the calibration concerns were partially justified and that some of the initial alarm was overstated. But it did not make the problem go away. Not remotely. Because even after removing the objects that turned out to be misidentified, even after updating the calibration, even after accounting for every known source of error, the remaining population of early galaxies was still far too abundant and far too massive to fit the models. Researchers at the University of Texas at Austin, led by graduate student Katherine Swarowski, conducted a systematic study that separated the genuine early galaxies from the objects that were being brightened by black hole activity. Their conclusion, published in late 2025, was carefully worded but significant. The standard model of cosmology was not broken. But there were still roughly twice as many massive galaxies in the early universe as the model predicted. The crisis had been downgraded from existential to serious. But serious, in this context, still means that something about the early universe allowed galaxies to form faster, larger, and more efficiently than anything in our current framework can explain. And the universe breakers were only the beginning. As Webb surveys expanded through 2023, 24, and 25, astronomers began cataloging a new and deeply puzzling population of objects scattered throughout the early universe. They appeared in image after image, tiny, intensely red, point-like sources that did not look like any known class of galaxy or star. Researchers started calling them little red dots. The little red dots created a specific problem. They were compact, suggesting small physical size, but they were extraordinarily bright, suggesting enormous energy output. When scientists tried to model them as galaxies, the stellar densities required were absurd. You would need stars packed so tightly that the night sky of such a galaxy would be blazingly bright. When scientists tried to model them as active black holes, the masses required were enormous, far too large for objects existing when the universe was less than 1 billion years old. By 2025, the list of identified little red dots had grown into the hundreds. A team at the University of Missouri identified 300 candidate objects in a single study using Webb's infrared cameras and advanced dropout techniques. The objects were brighter than any model predicted for their epoch. Some appeared point-like, suggesting they were powered by compact sources like black holes. Others showed hints of extended structure, suggesting they might be genuine galaxies undergoing star formation at incomprehensible rates. The most dramatic case arrived in mid-2024, when researchers using nearly 60 hours of Webb's spectrographic time obtained detailed spectra from thousands of distant galaxies. Among them was an object so extreme it was given its own nickname, the Cliff. Its spectrum indicated a concentration of mass so large and at such an early epoch that it forced researchers to reconsider their models entirely. While the little red dots consumed much of the theoretical attention, other discoveries were accumulating alongside them, each one adding a different kind of pressure to the standard picture. In early 2025, a team of astronomers announced the discovery of a galaxy they nicknamed the Big Wheel. It was not the most distant object Webb had found. It was not the most massive. What made it remarkable was its shape. The Big Wheel was a large spiral galaxy, complete with well-defined spiral arms and a coherent rotational structure, and it existed within the first 2 billion years of the universe's history. That might not sound surprising until you understand what spiral structure requires. A spiral galaxy is not a random clump of stars. It is a dynamically organized system in which stars, gas, and dust orbit a central mass in a flattened disk, with density waves propagating through the disk to create the characteristic arm pattern. Building a spiral takes time. The disk must settle, the orbits must stabilize. The density wave pattern must emerge from the gravitational interactions of billions of individual stars. In the modern universe, spiral galaxies are mature objects that have had billions of years to reach their current configuration. Finding one fully formed within the first 2 billion years implied that the gravitational settling process, the transformation from chaotic clump to ordered rotating disk, happened far more rapidly than models predicted. The Big Wheel was not just massive too early, it was organized too early, structured too early, calm too early. Themia Nanayakara of Swinburne University of Technology, one of the researchers who discovered it, pointed out that at such an early epoch, you would expect a massive galaxy to be elliptical, with a smooth, featureless shape born from chaotic mergers. Instead, the Big Wheel had the kind of geometric order that was supposed to require billions of years of dynamical evolution. It was as if the universe had skipped several chapters of its own story. Around the same time, another study identified roughly 70 heavily dust-obscured galaxies at extreme distances, galaxies so shrouded in dust that earlier instruments had missed them entirely. These were not little red dots. They were large, actively star-forming systems hidden behind thick veils of their own dust, visible only in the longer infrared wavelengths where Webb excels. The significance was statistical. 70 dust-rich galaxies in a single survey field suggested a far larger total population scattered across the full sky. If these objects were representative, the total number of massive, actively star-forming galaxies in the early universe was substantially higher than any census conducted before Webb had indicated. The universe was not only building galaxies faster than expected, it was building dusty, chemically enriched, industrially active galaxies in quantities that existing surveys had completely missed. Then, there were the dead ones. Webb found massive galaxies in the early universe that had already stopped forming stars. These objects, sometimes called quiescent or quenched galaxies, contained billions of solar masses worth of stars, but showed no signs of ongoing star formation. Their stellar populations were aging. Their gas supplies were depleted or expelled. They were, for all practical purposes, retired, sitting in the early universe like elderly cities in a landscape that was supposed to be populated entirely by construction sites. This was the mirror image of the too much, too early problem, not just premature birth, but premature death. The standard model struggled to explain how galaxies could assemble so quickly. Now, it also had to explain how some of those rapidly assembled galaxies had already shut down their star formation within the same narrow time window. Whatever mechanism was building galaxies faster than expected was also, in some cases, killing them faster than expected. The early universe was not simply ahead of schedule. It was running through its entire evolutionary sequence, from formation to maturity to quiescence, in a fraction of the time the models allotted for the first step alone. Several explanations were proposed. Feedback from active supermassive black holes at the centers of these galaxies might have heated or expelled the gas needed for continued star formation. An extraordinarily intense initial burst of star formation might have consumed the available gas supply in a single episode, leaving nothing for subsequent generations. Environmental effects, including interactions with neighboring galaxies or with the hot gas filling early galaxy clusters, might have stripped gas from these systems prematurely. Each of these mechanisms is physically plausible. None of them had been predicted to operate at such early epochs with such efficiency. The existence of dead galaxies in the young universe was not just an anomaly. It was evidence that the tempo of cosmic evolution in the first billion years was fundamentally different from what the standard framework described. A team from the Max Planck Institute and Penn State University proposed a radical explanation. The little red dots might not be conventional galaxies at all. They might represent an entirely new class of object, a supermassive black hole in an early phase of formation, surrounded by a thick envelope of gas that is simultaneously being consumed and radiating enormous amounts of energy. The researchers called these hypothetical objects black hole stars. In this model, the black hole at the center is swallowing material so rapidly that the surrounding gas puffs up into a massive glowing atmosphere that mimics many of the properties of a galaxy without actually being one. If correct, these black hole stars would represent the infancy stage of the supermassive black holes that sit at the centers of nearly all large galaxies today, including our own. This is a candidate explanation, not a confirmed one. The data is still being analyzed. But the fact that an entirely new class of astrophysical object had to be hypothesized to explain what Webb was seeing tells you something about the scale of the mismatch between prediction and observation. While the little red dots were being debated, Webb kept pushing the boundary of how far back it could see. And what it found at the very edge of the observable universe deepened the unease. In January of 2026, NASA and ESA jointly announced the confirmation of the most distant galaxy ever detected. Designated MOM Z14, this galaxy was observed as it appeared just 280 million years after the Big Bang. That is an almost impossible sentence to absorb. The universe is 13.8 billion years old. 280 million years represents roughly 2% of that total age. Webb was seeing a galaxy that existed when the cosmos was barely past its infancy, a window so early that the first stars themselves could only have been burning for a few tens of millions of years at most. MOM Z14 was not supposed to look the way it did. It was brighter than expected, more compact than expected, and more chemically enriched than expected. The galaxy showed elevated levels of nitrogen and other heavy elements at abundances that implied an unexpectedly advanced chemical history for an object so young. The full significance of that chemical signature and why it puts such severe pressure on the standard timeline is something we will return to shortly. For now, the point is simpler. MOM Z14 was not just distant. It was already chemically complex at an epoch when complexity was supposed to be barely getting started. Rohan Naidu of the Massachusetts Institute of Technology, the lead author of the study, described the finding directly. With Webb, he said, we are able to see farther than humans ever have before, and it looks nothing like what we predicted. His colleague, Jacob Shen, a postdoctoral researcher at MIT, put it more sharply. There is a growing chasm between theory and observation related to the early universe, he said, which presents compelling questions to be explored going forward. A growing chasm. That phrase matters. It is not the language of a single anomaly. It is the language of a systematic trend. One unexpected galaxy can be a fluke. A dozen can be a calibration issue. But when the pattern persists across multiple surveys, multiple instruments, multiple research teams, and multiple epochs of the early universe, the conversation shifts from "is this real?" to "what does this mean?" And MOM Z14 was not alone. It was one of a growing population of surprisingly bright galaxies at extreme distances. Webb had, by that point, confirmed that such galaxies were appearing at rates roughly 100 to 200 times higher than theoretical models had predicted before its launch. 100 to 200 times. That is not a minor adjustment. That is not a refinement of existing parameters. That is a gap so wide that it demands either a fundamental change in how we model star and galaxy formation in the early universe, or a fundamental change in the cosmological framework itself. The response from the theoretical community has been vigorous but fragmented. Some researchers propose that the first generations of stars were far more massive than previously assumed, burning hotter and shorter and producing heavier elements faster. Others suggest that star formation in the early universe was simply more efficient, converting gas into stars at rates that modern galaxies cannot match. Others point to the role of black holes, arguing that active galactic nuclei in the early universe contributed light that inflated the apparent brightness and mass of these young galaxies. Each of these proposals has merit, each has problems, and none of them, individually or collectively, has yet produced a complete explanation for everything Webb is seeing. There is another discovery from 2026 that adds a different dimension to the problem. In early 2026, a team at Texas A&M University, using Webb data, identified an ongoing merger event involving at least 5 galaxies when the universe was barely 800 million years old. The discovery added yet another dimension to the emerging pattern. The early universe was not only forming individual galaxies faster than expected, it was already entangling them in the complex gravitational interactions that were supposed to take billions of additional years to develop. The full implications of that finding, particularly what it reveals about chemical enrichment on scales larger than any single galaxy, will become clear shortly. Then there is the dark matter question. In January of 2026, a team, including researchers at UC Riverside, published one of the most detailed high-resolution maps of dark matter distribution ever produced, using Webb data from the Cosmos field. The map contained roughly 10 times more galaxies than previous ground-based surveys and twice as many as Hubble's coverage of the same region. It revealed new clumps and structures in the dark matter distribution that were previously invisible, and confirmed that ordinary matter traces the underlying scaffolding of dark matter with striking fidelity. But it also revealed that dark matter structures in the early universe may have been more complex and more tightly organized than the standard cold dark matter model predicts. A separate study published in Nature Astronomy used Webb observations of elongated young galaxies to argue that the data fit warm or wave dark matter scenarios better than the conventional cold dark matter model, suggesting that the very nature of dark matter, the invisible substance that constitutes 85% of all matter in the universe, might need to be reconsidered. Step back and consider what all of this means together. Webb did not find one anomaly. It found a pattern. A pattern of the early universe being more complex, more structured, more chemically mature, and more gravitationally active than the models said it should have been. This pattern does not appear in one observation or one survey. It appears across multiple independent data sets, gathered by different instruments, analyzed by different teams, using different methods, and pointing to the same conclusion. The early universe was not the simple, primitive place the standard model described. It was busy. It was already building massive galaxies, feeding enormous black holes, merging gravitationally bound systems, distributing heavy elements, and organizing dark matter into structures that look more complex than anyone anticipated. And here is what connects this back to the question of scale. When we talk about the scale of the universe, we are not just talking about size. We are talking about the relationship between distance and time. We are talking about what you find when you look across billions of light years. The comfortable version of scale says that the further you look, the simpler things get. You peel back the layers of cosmic history and find younger, smaller, less organized structures. The universe gets more primitive as you approach its origin. Scale is orderly. Depth reveals simplicity. Webb inverted that expectation. The deeper it looked, the more complexity it found. Not everywhere, not in every object, but in enough objects, at enough distances, across enough of the sky, that the trend is unmistakable. The early universe was doing things that should not have been possible in the time available. And if the time was not sufficient, then either the processes were faster than we understand, or the timeline itself is not what we think it is. This is where scale stops being a comfortable number and starts becoming a problem. Because the models that predict what should exist at each distance are the same models that tell us how old the universe is, how big it is, and how it has evolved from the Big Bang to the present. If the predictions at great distance do not match the observations at great distance, then something in the model connecting distance to time, to structure, is incomplete. Webb did not just see farther, it saw differently, and what it saw does not fit the story we built to explain it. The question was no longer, how far can we see? The question was, why does what we see not match what we expected? And answering that question requires confronting a set of cracks in the foundation of modern cosmology that go far deeper than any individual galaxy or any individual observation. Those cracks have a name, and they have been widening for years. Webb just made them impossible to ignore. There is a specific kind of scientific discomfort that is different from being wrong. Being wrong is simple. You had an answer, and the answer turned out to be incorrect. You replace it and move on. The discomfort that has settled over cosmology since Webb began delivering data is not that. It is the discomfort of having a framework that still works for most things, but fails precisely where it matters most. The standard model of cosmology has not collapsed. It still accurately describes the large-scale structure of the universe, the behavior of galaxies at moderate distances, and the general history of cosmic expansion. What it cannot do, as of right now, is explain what the universe looks like at the very beginning. And the very beginning is exactly where questions about scale, origin, and structure converge. To understand why the cracks are so significant, you need to understand what the standard model actually predicts about the early universe and why those predictions are so specific. Lambda CDM is not a vague sketch. It is a quantitative framework with precise numerical outputs. Given a set of input parameters, including the density of matter, the density of dark energy, and the rate of expansion, the model produces exact predictions about what the universe should look like at every stage of its history. How many galaxies should exist at a given epoch? How massive they should be? How quickly they should be forming stars? What chemical elements should be present and in what abundances? These are not rough estimates. They are calculated values that can be compared directly against observations. For decades, the observations matched. Not perfectly in every case, but within the expected range of statistical variation. The cosmic microwave background, the distribution of galaxies at moderate distances, the ratios of light elements formed during the first few minutes after the Big Bang, all of these checked out. The model was tested repeatedly, and it passed. That is why the scientific community trusted it. That trust was earned. What Webb has done is test the model in a regime where it had never been tested with this level of precision before. The first 500 million years of cosmic history. And in that regime, the model's predictions are not matching the observations. The mismatch is not subtle. It is not hiding inside error bars. It is staring back from image after image, spectrum after spectrum, in data gathered by multiple independent teams using different methods and arriving at the same conclusion. Consider what it means for a galaxy to contain 10 billion solar masses of stars when the universe is only 500 million years old. Stars do not appear instantaneously. The process of star formation begins with gas, primarily hydrogen and helium left over from the Big Bang, slowly collapsing under gravity into denser and denser regions until the pressure and temperature at the center become high enough to ignite nuclear fusion. That process takes millions of years, even under ideal conditions. But before the gas can collapse, something has to create the density perturbations that seed the collapse. In the Standard Model, those seeds are provided by dark matter, which clumps together first under gravity and then draws ordinary matter into the gravitational wells it creates. The dark matter has to clump, the ordinary matter has to fall in, the gas has to cool, the stars have to form. The first generation of stars has to live, die, and explode, scattering heavier elements into the surrounding medium. Then the process repeats with enriched gas, forming second-generation stars with more complex chemistry. Each cycle takes tens of millions of years. To build a galaxy with 10 billion solar masses worth of stars within the first 500 million years requires every one of those steps to happen faster than the models say they can. Not slightly faster, dramatically faster. The efficiency of star formation would need to be several times higher than anything observed in the modern universe. Some theorists have proposed that this is exactly what happened. The early universe was denser, the gas was more concentrated. The conditions were different enough that star formation operated in a mode that does not exist today. This is plausible. It is being actively modeled. But it requires revising a fundamental assumption embedded in every simulation of galaxy formation ever run, that the physics governing how gas turns into stars has been roughly consistent across cosmic time. If the early universe operated under a different star formation regime, then the models need to be rebuilt from the ground up for that epoch. That is not a small adjustment. That is a foundational change to how we calculate cosmic structure formation. And star formation efficiency is only one piece of the puzzle. The chemical enrichment problem is arguably more severe. When Webb observed galaxy MOM Z14 at a look-back time of 13.5 billion years, it detected elevated nitrogen abundances. Nitrogen is not a primordial element. It was not created in the Big Bang. It is manufactured inside stars through a process called the CNO cycle, which operates in stars more massive than roughly 1.5 times the mass of our Sun. Those stars must form, burn through their fuel, and die, either in supernovae or through gentler mass loss processes, before the nitrogen they created can be released into the surrounding gas and incorporated into the next generation of stars. For nitrogen to appear in detectable quantities in a galaxy only 280 million years after the Big Bang, several complete stellar life cycles must have already occurred. The most massive stars burn through their fuel in as little as a few million years, which helps. But even with the fastest possible stellar turnover, the timeline is extremely tight. You need the first stars to form almost immediately after conditions allow it, live and die rapidly, enrich the gas, and then have subsequent generations repeat the process multiple times within a window so narrow that every step must proceed at maximum possible speed. It is not impossible, but it pushes the physics to its limits. And when multiple galaxies at similar distances show similar chemical signatures, the explanation must be systematic rather than coincidental. This pattern, complexity appearing earlier than predicted, does not stop at galaxies and chemistry. It extends to the large-scale structures that galaxies inhabit. In early 2026, a team using Webb data discovered a multi-galaxy merger system roughly 800 million years after the Big Bang, involving at least 5 galaxies in close gravitational interaction. Mergers like this are common in the modern universe, where galaxies have had billions of years to drift into each other's gravitational influence. Finding a tightly packed merger system this early means that multiple galaxies had already formed, grown massive enough to attract each other, and begun the process of gravitational interaction within a cosmological window where the models expected to find mostly isolated protogalaxies still assembling their first stars. The merger was also redistributing heavy elements into the space between the galaxies, enriching the intergalactic medium in a process that was not expected to be significant until much later in cosmic history. This matters because the chemical state of the intergalactic medium directly affects the next generation of galaxy formation. Enriched gas cools more efficiently than pristine gas, which means it can collapse into stars more readily. If the early universe was already enriching its intergalactic medium through galaxy mergers, then subsequent galaxy formation would have been accelerated by the chemical groundwork laid by these early interactions. The timeline of structure formation does not just shift earlier, it potentially accelerates because earlier complexity enables faster subsequent complexity. Now, layer the Hubble tension on top of all of this. Because the expansion rate discrepancy is not a separate problem. It is connected to everything described above, and Webb's role in confirming it is among its most consequential contributions to modern cosmology. The Hubble constant, designated Higgs 0, is the number that describes how fast the universe is expanding right now. It is not a speed in the ordinary sense. It is a rate. For every megaparsec of distance between two objects, space between them is expanding by a certain number of kilometers per second. A megaparsec is approximately 3.26 million light-years. The value of Higgs 0 determines the relationship between distance and recession velocity across the entire observable universe. It is the conversion factor that connects what you see in a telescope to the physical reality of cosmic expansion. There are two primary ways to measure this number, and they give different answers. The first method uses the cosmic microwave background, the oldest light in the universe, as a starting point. Scientists measure the properties of the cosmic microwave background with extraordinary precision, most notably using data from the European Space Agency's Planck satellite. From those measurements, they extract the conditions of the early universe, its density, its composition, and its expansion rate at the time the cosmic microwave background was released, roughly 380,000 years after the Big Bang. Then, they use the standard model of cosmology to extrapolate forward in time, calculating what the expansion rate should be today, given those initial conditions and the known physics of cosmic evolution. This method yields a value of approximately 67 to 68 kilometers per second per megaparsec. The Atacama Cosmology Telescope, in its final data release in late 2025, independently confirmed this value using its own high-precision measurements of the cosmic microwave background. The second method measures the expansion rate directly, using objects in the relatively nearby universe whose distances can be determined through independent means. This approach is called the cosmic distance ladder. It starts with objects whose distances can be measured geometrically, then uses those calibrated distances to determine the distances of slightly farther objects, and so on, step by step, reaching outward across hundreds of millions of light-years. The final rung of the ladder connects these calibrated distances to the recession velocities of galaxies, from which Higgs 0 can be calculated directly. This method, refined over decades by teams led by Nobel laureate Adam Rees and others, consistently yields a value of approximately 73 kilometers per second per megaparsec. 68 versus 73. The gap sounds small. It is not. The difference represents roughly an 8% discrepancy in the fundamental expansion rate of the universe. In a field where measurements are routinely refined to fractions of a percent, 8% is enormous, and the statistical significance of the discrepancy has grown steadily as both methods have been refined. As of late, 2025, the disagreement has reached 5 sigma, the threshold that physicists use to declare a result statistically certain. At 5 sigma, the probability that the discrepancy is due to random chance is less than 1 in 3.5 million. This is where Webb's contribution becomes critical. One of the leading explanations for the discrepancy was systematic error in the distance ladder. Specifically, critics suggested that the distances to Cepheid variable stars, the workhorses of the local distance measurement, might be corrupted by crowding effects. Cepheids in distant galaxies are often embedded in dense stellar fields. If the light from nearby unrelated stars blends with the Cepheid's light, the star appears brighter than it really is, and its distance is underestimated. This crowding effect, if significant, could inflate the local measurement of H0, creating a false tension with the cosmic microwave background value. Webb was perfectly positioned to test this. Its infrared resolution is sharp enough to separate individual stars in crowded fields where Hubble saw only blended light. In 2024 and 25, the SHOES team, led by Rees, used Webb to re-observe the same Cepheids that Hubble had measured. The result was unambiguous. Webb's measurements matched Hubble's. Crowding was not corrupting the data. The local value of H0, approximately 73, was confirmed to be robust. Simultaneously, independent teams, using entirely different distance indicators, produced values consistent with the local measurement. A study, published in early 2025 by Dan Skolnick of Duke University, used the distance to the Coma cluster, measured through a method independent of Cepheids, to calibrate the distance ladder. The result was a Hubble constant of approximately 76.5, even higher than the SHOES value and even further from the cosmic microwave background prediction. Skolnick described the result bluntly. This is saying, to some respect, that our model of cosmology might be broken. The word broken carries weight in this context. Skolnick is not a contrarian. He is one of the leading observational cosmologists in the world. When he uses that word, he is not being dramatic. He is describing a situation where the two most precise and most independent methods of measuring a single fundamental property of the universe produce answers that are incompatible with each other at a level of confidence that rules out statistical coincidence. To understand what this means for scale, consider what the Hubble constant actually determines. If H0 is 73, the universe is expanding faster than the standard model predicts. A faster expansion implies a younger universe, because you need less time to reach the current size if the expansion rate is higher. Using the local measurement, the universe would be closer to 13 billion years old rather than 13.8 billion. That is a difference of roughly 800 million years. If the even higher value measured by Skolnick's team holds, the gap widens further. It does not just change a number on a page. It changes every calculation that depends on the age of the universe, including the amount of time available for structures to form, for stars to evolve, and for galaxies to assemble. Here is where the connection snaps into focus. The early galaxies that Webb found, the ones that are too massive and too mature for their supposed epoch, are calibrated against a timeline that assumes an age of 13.8 billion years. If the actual age is closer to 12.8 billion years, those galaxies had even less time to form than the current calculations assume. The problem does not get better with a faster expansion rate. It gets worse. The window for early galaxy formation shrinks, and the mismatch between prediction and observation widens. Some researchers have explored the opposite direction. Perhaps new physics in the early universe, such as a brief phase of extra dark energy operating before the cosmic microwave background was released, could reconcile the two measurements by changing the predicted expansion rate at early times. This approach, called early dark energy, is one of the most actively studied modifications to the Standard Model. If a burst of additional dark energy existed during the first few 100,000 years and then disappeared, it would alter the sound horizon, the characteristic scale imprinted in the cosmic microwave background, in a way that shifts the predicted Hazero upward toward the local value. But early dark energy models have their own problems. They tend to conflict with other observations, including measurements of how matter clumps together at large scales, a separate tension known as the Sate tension. Fixing one crack sometimes opens another. The crack that early dark energy sometimes opens has a name. It is called the Sate tension, and it deserves attention in its own right because it represents a second, independent fracture in the Standard Model that complicates every attempt to resolve the first. The Sate parameter, sometimes written as sigma 8, measures how clumpy matter is on large scales. Specifically, it quantifies the amplitude of matter density fluctuations in spheres with a radius of 8 megaparsecs, roughly 26 million light-years. The Standard Model predicts a specific value for Sate based on the initial conditions measured in the cosmic microwave background. If you know how clumpy the universe was at age 380,000 years, and you know the physics that governs how those clumps grow under gravity over the following 13 billion years, you can calculate how clumpy the universe should be today. When astronomers measure the actual clumpiness of the modern universe using gravitational lensing surveys and galaxy clustering data, they get a value that is slightly but persistently lower than the Standard Model predicts. The universe today is less clumpy than it should be. Matter has not gathered into structures as aggressively as the models expected. This might sound like a minor bookkeeping issue. It is not. The Sate tension has reached a level of statistical significance, roughly 2 to 3 sigma, depending on the measurement, that is lower than the Hubble tension's 5 sigma, but substantial enough to be taken seriously. More importantly, the two tensions interact in ways that create a kind of theoretical trap. Many of the proposed modifications to the Standard Model that are designed to raise the predicted Hubble constant, bringing the cosmic microwave background prediction into agreement with the local measurement, also change the predicted growth rate of structure. And they tend to change it in the wrong direction, making the Sate tension worse rather than better. Early dark energy is the clearest example of this problem. Adding a burst of extra dark energy before the cosmic microwave background was released increases the predicted expansion rate at early times, which shifts the derived Hubble constant upward. But it also changes the rate at which density perturbations grow, typically making the predicted universe clumpier than it already appears to be. You close one gap and widen another. This interconnection is what makes the current situation feel less like a collection of separate puzzles and more like a single, deep structural problem. The Hubble tension and the Sate tension are not independent failures. They are symptoms of the same underlying framework being tested at the limits of its accuracy. And the fact that attempts to fix one tend to worsen the other suggests that the resolution will not be a simple patch. It will require a modification that simultaneously accounts for both the expansion rate discrepancy and the structure growth discrepancy, a modification whose shape is not yet clear. In September of 2025, over 130 researchers gathered in Corfu, Greece, for a conference titled Tensions in Cosmology. The meeting report, published in Nature Astronomy in early 2026, summarized the state of the field with unusual candor. The Hubble tension was not the only anomaly under discussion. Multiple tensions, multiple mismatches between the Standard Model's predictions and the observations being gathered by Webb, by the Dark Energy Spectroscopic Instrument, by the Atacama Cosmology Telescope, and by other facilities, were accumulating. The report characterized the situation as a growing set of tensions with the standard model of cosmology. Not one tension, a growing set. One of the newest and most consequential additions to that set arrived from an instrument that is not a telescope at all, but a robotic factory for measuring distances. The Dark Energy Spectroscopic Instrument, known as DESI, is mounted on a 4-meter telescope at the Kitt Peak National Observatory in Arizona. Its purpose is to map the three-dimensional distribution of galaxies across roughly 1/3 of the sky, measuring the distances and recession velocities of tens of millions of individual galaxies over a 5-year survey. By tracking how the large-scale structure of the universe has evolved over the past 11 billion years, DESI can constrain the behavior of dark energy with unprecedented precision. In 2024 and 25, DESI released its first major results. They were startling. The data suggested that dark energy may not be constant over time. This matters enormously because the cosmological constant, the lambda in lambda CDM, is defined as a fixed energy density. It does not change, it does not evolve. It is the same everywhere and at all times. This assumption is one of the foundational pillars of the Standard Model. If dark energy is actually varying, growing stronger or weaker across cosmic history, then the expansion history of the universe is different from what lambda CDM assumes. And if the expansion history is different, then every derived quantity that depends on it, including the age of the universe, the distances to faraway objects, and the predicted growth rate of structure, shifts accordingly. The DESI results are preliminary. The statistical significance is not yet at the level required to declare the cosmological constant dead. But the trend in the data points away from a constant and toward a dark energy component that was weaker in the past and has grown stronger over time. If confirmed by subsequent data releases, this would represent a fundamental change in our understanding of the dominant component of the universe, the force responsible for roughly 68% of its total energy content. For the question of scale, the implications are direct. If dark energy is evolving, then the expansion rate of the universe has not followed the smooth trajectory that the Standard Model describes. There may have been epochs where expansion was slower or faster than currently assumed. The distances derived from redshift measurements, the ages assigned to distant galaxies, and the volume of the observable universe itself would all need to be recalculated under the revised expansion history. This does not mean the numbers would change dramatically. The modifications being considered are subtle, adjustments of a few percent in key parameters rather than wholesale revisions. But a few percent, applied to a quantity like the age of the universe or the diameter of the observable horizon, represents hundreds of millions of years or billions of light years. At the scales cosmology operates on, small fractional changes translate into enormous absolute shifts. The DESI results also interact with the Hubble tension in ways that are still being explored. If dark energy was weaker in the past, the expansion rate at early times would have been different, which could change the predicted value of the Hubble constant derived from the cosmic microwave background. Whether this change is in the right direction and of the right magnitude to resolve the tension is an open question. Early analyses suggest it helps, but does not fully bridge the gap. What the DESI results add to the broader picture is a sense that the problem is not confined to the early universe. The Hubble tension concerns a mismatch between early and late measurements. The early galaxy problem concerns unexpected structures in the first billion years. The SATE tension concerns the growth of structure across cosmic history. And now DESI suggests that dark energy itself, the dominant force shaping the universe's large-scale evolution, may be behaving differently than assumed across the entire timeline. The cracks are not concentrated in one epoch or one measurement. They are distributed across the full span of cosmic history, appearing wherever precision instruments push the standard model hard enough to reveal its limits. This is what transforms the Hubble tension from a measurement puzzle into a structural problem. The expansion rate discrepancy does not exist in isolation. It exists alongside the early galaxy problem, the chemical enrichment problem, the early merger problem, and the dark matter structure problem. Each of these could potentially be explained individually by adjusting parameters within the standard model or by invoking specific astrophysical mechanisms. But they all point in the same direction. They all suggest that the early universe was more complex, more active, and more structured than the framework predicts. And the framework they challenge is the same framework that defines our understanding of cosmic scale. Because scale, in cosmology, is not a raw measurement, it is a derived quantity. The diameter of the observable universe, 93 billion light-years, is calculated using the standard model. The age of the universe, 13.8 billion years, is derived from the same framework. The distances to individual galaxies, the look-back times assigned to Webb's observations, the relationship between redshift and physical distance, all of these depend on the parameters of lambda CDM. If the model is incomplete, if its predictions fail at early times, if the Hubble constant is genuinely inconsistent between methods, then the numbers we use to describe cosmic scale are not wrong in the sense of being fabricated. They are uncertain in a way they were not before. The confidence interval has widened. The error bars have grown. And in cosmology, wider error bars on the fundamental parameters mean wider uncertainty about literally everything that depends on those parameters. There is an analogy that captures this situation more precisely than any technical description. Imagine you are navigating a ship across an ocean using a coordinate grid printed on a chart. For years, the grid has been reliable. Every island, every reef, every current matched the grid's predictions. You trusted the grid, not because you had faith in it, but because it kept being right. Then you sail into new waters, farther from shore than anyone has been before, and in these new waters, the islands are not where the grid says they should be, not wildly off. Not on the opposite side of the ocean, but shifted, consistently shifted, by amounts that are small enough to be confusing, but large enough to be dangerous. The grid is not useless. It still gives you the general direction. But the precise positions it assigns to objects in this region are unreliable, and you do not yet have a corrected grid to replace it. That is what is happening to the cosmological coordinate system right now. The grid, lambda CDM, still works in the well-charted waters close to home. Galaxies at moderate distances behave as expected. The large-scale structure of the nearby universe matches the predictions. The cosmic microwave background is consistent with the model's parameters. But at the edges, in the deep waters that Webb has opened for the first time, the positions are off. The objects are not where the grid says they should be. They are too massive, too mature, too chemically enriched, too structurally organized for the coordinates they have been assigned. The grid is not broken in the sense that it gives random answers. It is broken in the sense that it gives answers that are systematically wrong in one direction, a direction that consistently implies more complexity, more activity, and more structure at early times than the grid accounts for. That systematic bias is what separates this from a measurement error. Measurement errors are random. They scatter in all directions. Systematic offsets point somewhere, and the direction they point is toward a universe whose early history was fundamentally more dynamic than the standard framework describes. Consider what this does to the experience of looking at a Webb image. When you see a deep field photograph, filled with thousands of galaxies stretching back across 13 billion years of cosmic history. You are seeing a picture whose interpretation depends entirely on the model used to convert light into distance, distance into time, and time into physical meaning. If the model is secure, the picture is reliable. The distances are real, the ages are accurate, the story is coherent. If the model has cracks, the picture becomes less certain, not wrong, not fictional, but less firmly anchored than it appeared. The same photons arrive at the telescope, but what they mean depends on a framework that is now under strain. This is the dimension of scale that most popular accounts miss entirely. When people hear that Webb has revealed the true scale of the universe, they imagine bigger numbers, more galaxies, greater distances. And those things are true, but the deeper shift is epistemological. It is about the relationship between observation and understanding. For decades, deeper observation produced better understanding. Better telescopes confirmed and refined the standard model. The circle closed. You looked deeper, and the universe made more sense. Webb has disrupted that cycle. For the first time in modern cosmological history, looking deeper has made the universe make less sense. Not in a dramatic, everything is wrong sense, but in a persistent, quietly accumulating sense where each new observation at extreme distance introduces another data point that the existing framework struggles to accommodate. The models have not failed entirely, but they are straining, and the strain is greatest precisely at the depths where scale, time, and origin converge. There is one more dimension of this problem that must be addressed before moving to the final implications. It concerns not what Webb sees, but what it cannot see, and what that invisible boundary means for the meaning of scale itself. The observable universe is 93 billion light-years across. That is the sphere from which light has had time to reach us since the Big Bang, accounting for the expansion of space during the journey. But the observable universe is not the universe. It is only the part we can see. Beyond the edge of the observable universe, space continues. Galaxies exist, stars burn, physics operates. But the light from those regions has not had enough time to reach us, and due to the accelerating expansion of space, some of it never will. How much larger is the total universe than the observable one? Current estimates, based on measurements of the universe's geometry, which appears to be flat to within the precision of our instruments, suggest that the total universe is at least 250 times larger in radius than the observable portion. Some calculations put the minimum diameter at roughly 7 trillion light-years. Others suggest it could be effectively infinite. The honest answer is that we do not know. The geometry measurements constrain the lower bound, but cannot determine the upper bound. The universe could be 1,000 times larger than what we see. It could be 1,000,000 times larger. It could go on without limit. This means the 93 billion light-year sphere we call the observable universe is not a representation of the cosmos. It is a tiny sample, a keyhole view. And everything we know about the universe, every model we have built, every parameter we have measured, is based on observations made within this sample. The standard model of cosmology assumes that the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction and at every location. This assumption, called the cosmological principle, is supported by observations within our sample. The cosmic microwave background is remarkably uniform. The distribution of galaxies at large scales is statistically similar in every direction, but those observations can only confirm homogeneity within the volume we can see. They cannot confirm it beyond. This is normally a background assumption, something physicists acknowledge but do not worry about in practice. It becomes more urgent when the model that assumes homogeneity begins to show cracks. Because If the standard model fails to describe what we observe at the earliest epochs within our sample, one possible explanation is that the assumption of perfect homogeneity is itself an oversimplification. The universe within our observable volume may not be perfectly representative of the universe as a whole. Local variations in density, expansion rate, or dark energy could introduce biases in our measurements that mimic the tensions Webb has revealed. This is speculative. It is not the leading explanation, but it is being discussed in the literature, and it connects directly to the question of scale. Because if the observable universe is not a fair sample of the total universe, then every statement we make about cosmic scale is contingent. It applies to the volume we can see. It may not apply to the volume we cannot. The universe could be even stranger, even more varied, even less uniform than the already strange picture Webb is painting within our horizon. And this brings us to the deepest layer of the problem, the one that has not yet been fully articulated, the one that connects the Hubble tension, the early galaxy problem, the chemical enrichment mystery, the dark matter structure questions, and the limits of the observable universe into a single, coherent, and deeply unsettling realization about what the true scale of the universe actually means. The cracks are not in the telescope, they are in our model of reality, and the deepest implication has not been stated yet. There is a moment in every scientific revolution that does not arrive as a headline, it arrives as a feeling. A slow, settling recognition among the people closest to the data that the old picture is no longer adequate, but the new picture has not yet formed. It is not the exhilaration of discovery. It is not the despair of failure. It is something more disorienting than either. It is the feeling of standing between two frameworks, able to see the flaws in the one you are leaving, but unable to see the shape of the one you are approaching. That is where cosmology stands right now. Not in crisis, in the dramatic sense, not in collapse, in transition. And transitions, in science, are the most intellectually dangerous places to be, because the temptation to either panic or pretend nothing has changed is almost overwhelming. Both responses are wrong. What the moment actually requires is something much harder. It requires sitting with uncertainty and letting it teach you something about the nature of knowledge itself. Let us begin with a question that sounds simple but is not. What does it actually mean to say the universe is 93 billion light-years across? On the surface, it is a measurement, a number with units attached. You can write it down, compare it to other numbers, convert it into kilometers or miles or megaparsecs. It behaves like a fact. And in the strictest sense, it is one. The diameter of the observable universe, calculated from the parameters of the standard model of cosmology and the measured properties of the cosmic microwave background, is approximately 93 billion light-years. That calculation has been checked by independent teams using independent methods. The number is robust. But robust is not the same as simple. That number is not a measurement the way the height of a building is a measurement. You cannot stretch a tape measure across the observable universe. You cannot bounce a laser off the edge and time its return. The diameter of the observable universe is a derived quantity. It depends on a model. Specifically, it depends on the values of the cosmological parameters plugged into lambda CDM, the Hubble constant, the density of matter, the density of dark energy, the curvature of space. Change any one of those parameters, and the derived diameter changes with it. This is not a flaw in the method. It is how all cosmological measurements work. Every distance, every age, every statement about the scale of the universe is filtered through a model that converts raw observations into physical quantities. The observations themselves are just photons arriving at a detector. The meaning of those photons, what they tell you about distance and time and structure, is determined by the framework you use to interpret them. When the framework is stable and well-tested, this dependency is invisible. You trust the model. You trust the numbers. The derived quantities feel as solid as direct measurements. That is exactly where cosmology was before Webb. The standard model had been tested against decades of observations, and it passed. The parameters were precisely constrained. The derived quantities, including the diameter and age of the observable universe, felt settled. They were printed in textbooks. They were cited in documentaries. They had the weight of established fact. What Webb has introduced is not doubt in the measurements themselves. It is doubt in the stability of the framework through which the measurements are interpreted. If the Hubble constant is genuinely inconsistent between methods, then the parameters of the model are not as precisely constrained as they appeared. If the early universe contains structures that the model cannot account for, then the model's predictions are not as reliable as they seemed. And if the model is less reliable, then every quantity derived from it, including the diameter, the age, and the structural history of the observable universe, carries a wider band of uncertainty than it did 5 years ago. This is not a semantic point. It changes what the word scale means in a cosmological context. Before Webb, cosmic scale was essentially a settled coordinate system. You could point to a galaxy, state its distance in light years, assign it a look-back time, and describe where it sat in the history of cosmic evolution with reasonable confidence. The numbers were large, but they were stable. The map was fixed. After Webb, the map has begun to shift. Not dramatically, not in a way that changes everyday astronomy. A galaxy that was 10 billion light-years away last year is still approximately 10 billion light-years away now. But the confidence interval around that number has grown. The model uncertainty has increased. And at the extreme distances where Webb operates, where every observation probes the boundary between the known and the unknown, the uncertainty is largest. This creates a paradox that is central to the story. The most powerful telescope ever built, the instrument that sees farther and more clearly than anything before it, has produced a less certain picture of the universe rather than a more certain one. Not because the data is bad. The data is extraordinary. But because the data is revealing mismatches that cannot be resolved within the existing framework, and no replacement framework has yet emerged. In the history of science, this pattern is not new. It is, in fact, the signature of a paradigm in strain. The astronomer Tycho Brahe spent decades gathering the most precise astronomical observations of his era. His data was exquisite, his instruments were the finest available. And his measurements were what ultimately proved that the existing model of the solar system, the Ptolemaic model with Earth at the center, could not account for the observed positions of the planets. Brahe did not have a replacement. He proposed his own compromise model that placed Earth at the center but had the other planets orbiting the Sun. It was wrong. The correct framework, the Copernican-Keplerian model with the Sun at the center and planets moving in ellipses, required a conceptual leap that Brahe himself never made. The leap was made by others using his data. The analogy is not perfect. Lambda CDM is far more successful and far more precisely tested than the Ptolemaic model ever was. It is not going to be discarded wholesale. Whatever replaces or modifies it will almost certainly contain lambda CDM as a limiting case, the way Einstein's general relativity contains Newtonian gravity as a limiting case. The standard model works too well across too many domains to be simply wrong. But it may be incomplete. And the places where it appears incomplete are precisely the places where Webb is looking. The earliest epochs, the greatest distances, the boundary between observation and origin. There is a philosophical weight to this that deserves to be stated directly because it changes the meaning of the title of this story. When people hear the phrase, the true scale of the universe, they expect a number, a bigger number, a more impressive number, a number that makes the old numbers seem small. And Webb has delivered those numbers. The observable universe contains up to an estimated 2 trillion galaxies, though more recent assessments suggest the number may be lower. The total universe beyond the observable boundary may be at least 250 times larger in radius, and possibly infinite. The deepest observations reach back to within 280 million years of the Big Bang, a time so early that the universe had completed barely 2% of its current age. Those numbers are real, and they are staggering. But the true scale of the universe, as Webb is revealing it, is not primarily about those numbers. It is about something far more disorienting. It is about the growing distance between what we can observe and what we can explain. Every generation of telescopes in the history of astronomy has expanded the boundaries of the observable universe. Every expansion brought a corresponding expansion of understanding. Galileo's telescope revealed moons orbiting Jupiter, confirming that not everything orbited Earth. Larger telescopes revealed that the fuzzy nebulae in the sky were actually other galaxies, expanding the known universe from one galaxy to billions. Hubble showed that the universe was expanding, providing a coherent framework for understanding cosmic evolution. Each step outward was also a step toward greater comprehension. Seeing more meant knowing more. The two moved in tandem. Webb is the first major instrument to break that pattern. Seeing more with Webb has meant knowing less, in the specific sense that the new observations have introduced questions that the existing framework cannot answer. The universe at extreme distance does not behave the way the models say it should. The expansion rate does not reconcile between methods. The chemical and structural maturity of early galaxies exceeds the predictions. The dark matter distribution shows features that challenge conventional assumptions. Each of these findings is an observation that does not yet have a settled theoretical home. This is not a failure of science. It is science working exactly as it should. The entire purpose of building better instruments is to test the limits of current understanding. If Webb had confirmed every prediction of the standard model, it would have been a successful telescope, but a disappointing one. The most valuable outcome of any observation is a surprise, because surprises are where new understanding comes from. The history of physics is a history of surprises that broke existing frameworks and led to deeper ones. The ultraviolet catastrophe led to quantum mechanics. The constancy of the speed of light led to special relativity. The anomalous precession of Mercury's orbit led to general relativity. In each case, the old framework was not discarded. It was absorbed into a larger one that explained everything the old framework explained, plus the new observations that it could not. Something analogous may be happening now. The tensions that Webb has amplified, the Hubble tension, the early galaxy excess, the chemical enrichment puzzle, may be early signals of a modification to the standard model that preserves its successes while accounting for its failures. Early dark energy is one candidate. Modified dark matter models are another. Primordial magnetic fields affecting the cosmic microwave background have been proposed. The interaction between dark matter and dark energy might be more complex than the cosmological constant assumes. Each of these proposals is being tested against data. None has yet emerged as a clear solution. The field is in the uncomfortable middle stage, where the problems are better defined than the answers. And this brings us to the deepest layer of what Webb reveals about scale. Not the spatial scale of the universe, which is almost certainly larger than the observable volume and possibly infinite. Not the temporal scale, which stretches back 13.8 billion years to the Big Bang and possibly beyond into whatever preceded it, but the epistemic scale, the scale of the gap between what the universe is and what we understand about it. For most of human history, this gap was assumed to be closing. Every century brought more knowledge. Every instrument revealed more of reality. The trend pointed toward an eventual convergence, a point at which human understanding would fully encompass the physical universe. That assumption was never stated as a formal scientific claim. It was more of a cultural atmosphere, a background confidence that reality was fundamentally knowable and that the arc of science bent toward completeness. Webb challenges that assumption in a specific and measurable way. The telescope has not revealed that the universe is unknowable. It has revealed that the universe at its earliest and most distant stages is more complex than the best models predicted, and it has done so at a moment when those models were at the peak of their apparent precision. The standard model of cosmology was not a rough sketch. It was a tightly constrained quantitative framework with parameters measured to multiple decimal places. The fact that this framework is showing cracks precisely where Webb can see most clearly suggests that the relationship between observational power and theoretical understanding is not as straightforward as the history of astronomy had led us to believe. Greater observational reach has not simply extended the map, it has revealed that the territory is different from the map in ways the map did not anticipate, and the further you extend the reach, the more pronounced the differences become. That is the pattern. It is not a single anomaly, it is a trend, and the trend points in a direction that is genuinely humbling. Because the observable universe, as enormous as it is almost certainly a tiny fraction of the total. Using even the most conservative lower bound discussed earlier, the volume of the total universe would be roughly 15 million times larger than the volume we can observe. Everything we know, every parameter we have measured, every model we have built, is based on observations made within 1/15 millionth of the total volume, and the total volume may be far larger still, possibly infinite. What this means is that all of our cosmological knowledge, including the quantities that feel most settled, is based on a sample that may be unrepresentative. The cosmological principle, the assumption that the universe looks the same everywhere, is supported by observations within our sample. But it is an assumption, not a proven fact. If the universe is truly vast or infinite, then local variations in density, expansion rate, or the properties of dark energy could exist on scales larger than our observable horizon. Those variations would be invisible to us. We would have no way to detect them, and they could introduce biases in our measurements that mimic the very tensions Webb has revealed. This is not a leading explanation for the Hubble tension. Most cosmologists believe the resolution lies in modifications to the standard model or in astrophysical mechanisms that are not yet fully understood. But the mere possibility that our observable volume is an unrepresentative sample of a much larger cosmos introduces a layer of epistemic uncertainty that is fundamentally different from measurement error. It is not that our instruments are imprecise. It is that the volume of reality accessible to our instruments may be too small to capture the full range of physical conditions that exist. That is a statement about scale that no number can capture. The true scale of the universe is not 93 billion light-years, or 7 trillion light-years, or infinity. The true scale is the relationship between the vastness of what exists and the narrowness of what we can observe. And Webb, by pushing the boundary of observation to its current limit and finding that the limit reveals more questions than answers, has made that relationship viscerally real in a way it never was before. There is one final thought that follows from all of this, and it concerns the human position within the picture. For centuries, every major discovery in astronomy has diminished the perceived centrality of human beings. Copernicus removed Earth from the center of the solar system. telescopes revealed that the Sun is an ordinary star in an ordinary galaxy. Hubble showed that our galaxy is one of billions. The cosmic microwave background revealed that the universe is far older than human civilization and indifferent to its existence. Each step moved humanity further from the center and further from significance on a cosmic scale. This trajectory is sometimes called the Copernican principle, and it has been remarkably consistent. Webb extends this trajectory, but in a direction that is subtly different from what came before. Previous discoveries diminished humanity's spatial and temporal centrality. We are not at the center. We are not special. We are not old. Webb adds a new dimension to this diminishment. It diminishes our epistemic centrality. It suggests that we are not only small and peripheral in the universe, we may also be fundamentally limited in our ability to understand it. Not permanently limited, not hopelessly limited. Science is the most powerful tool for understanding reality that human beings have ever developed, and there is no reason to believe it has reached its limits. The tensions Webb has revealed will almost certainly be resolved, either through modifications to the standard model or through entirely new theoretical frameworks that explain the observations. The history of physics gives every reason for confidence that deeper understanding is possible. But the timeline of that understanding is not guaranteed. The resolution might take years. It might take decades. It might require instruments that have not yet been designed, observing phenomena that have not yet been predicted, using physics that has not yet been formulated. And in the meantime, the universe that Webb has revealed is one that resists the tidy narrative of progress that has characterized popular science communication for generations. The story is not simply that the universe is bigger than we thought. The story is that the universe is more structurally surprising than we thought, and that the deeper we look, the more surprising it gets. That is the true scale of the universe as James Webb has revealed it. Not a number, not a diameter, not a distance or an age. It is the growing awareness that observational power and theoretical understanding do not always advance together, that seeing farther into the cosmos may also mean seeing farther into the limits of our current frameworks. That the universe is not only vast but resistant to the kind of simple, progressive comprehension that our scientific culture has taught us to expect. The questions Webb has raised are not empty provocations. They are precise, testable, scientifically grounded problems that the next generation of instruments and theorists will work to solve. The Nancy Grace Roman Space Telescope, expected to launch in the coming years, will survey enormous volumes of sky with Hubble-level clarity, identifying thousands of the early bright galaxies that Webb first detected and providing the statistical samples needed to determine whether the early galaxy excess is real and how large it truly is. The Vera Rubin Observatory in Chile, with the largest digital camera ever built, will map billions of galaxies across the southern sky, tracing the growth of cosmic structure with a precision that could break the degeneracies in the Hubble tension. The European Space Agency's Euclid mission, already gathering data, will map the geometry of the universe across billions of light-years, testing whether dark energy is truly constant or whether it varies across time and space. Each of these instruments will bring new data to bear on the questions Webb has opened. The problems are not unanswerable, they are unsolved. But the fact that they are unsolved now, at a moment when the most powerful space telescope ever built is operating at the peak of its capabilities, is itself significant. It tells us something about where we are in the history of understanding. We are not at the end. We are not even close. We are at a moment where the tools have outpaced the theories, where observation has raced ahead of explanation, where the data is arriving faster than the frameworks can absorb it. And the universe, indifferent to our timelines and unconcerned with our comfort, keeps revealing itself in forms we did not anticipate. Galaxies that are too massive, too early. An expansion rate that contradicts itself, chemical enrichment that outpaces the clock, dark matter that clumps in ways the models do not predict. A cosmos that, the deeper you look, does not converge on a single coherent picture, but instead fractures into a set of interlocking puzzles whose solutions remain just beyond the reach of current understanding. That is not a failure, it is an invitation. The most honest thing science can say is also the most powerful. We do not yet know. The universe is bigger than our models. The past is more complex than our theories. The scale is not just a measurement, it is a challenge issued by reality itself to keep looking, keep questioning, and keep building frameworks worthy of what the instruments reveal. Webb was built to see the edge. It did, and what it found there was not an answer. It was a deeper question. A question about whether the universe will ever fully submit to the frameworks we build for it, or whether each new layer of observation will always reveal another layer of mystery beneath. The true scale of the universe is not how far it extends, it is how far it exceeds what we can currently explain. And right now, in the light arriving from 13 billion years ago, that distance is growing.